Hello MacroHard family, welcome back. So today we are going to discuss about proof of reserves. So last year during November, after the FTX collapse, the founder of Binance proposed an idea where every centralized exchange should give proof of reserves of their solvency. So today we are going to discuss how exactly proof of work works in centralized exchanges. So in order to understand proof of reserves, we need to understand two mathematical concepts. So the first concept is of Merkel trees, and in order to understand Merkel trees, we first need to understand hashes. So cryptographic hash is a function whose input can be any randomly sized bit string and its output is a fixed sized bit string, for example a 256-bit string. Now in the digital world everything is bit. For instance, if we take an image, at the end of the day it is a string of bits. If we take a video of fixed length, then again it's a string of bits. So therefore we can apply the hash function to any object like image, a number, a video, etc. However, the output of this hash function will be a fixed 256-bit string. Now, in order to understand the intuition behind the power of hashes, consider the following. So hash functions map a given input to an output which is randomly chosen between 0 and 2 raised to power 256. Now 2 raised to power 256 is a very big number. In fact, the number of sand particles on Earth are less than 2 raised to power 256. So one can imagine that hash functions map a given object to a randomly chosen sand particle on Earth. So as a consequence, if two objects are hashed, then the probability that both of them will be hashed to the same number is practically zero. So you can imagine yourself that what is the probability that I map two numbers randomly to sand particles on Earth and both of them exactly maps to the same sand particle. The probability is practically zero. Another consequence of hashes is that given the output hash, it is extremely difficult to find the input which actually provided the given output. So again, to intuitively think about this, so if I ask you to find an input such that its hash maps to this particular sand particle on Earth, so you can imagine that it will be extremely hard to find out of so many possibilities the particular input which will map to a particular sand particle on Earth. So now that you know the power of hash functions, let's try to understand Merkel trees. So we can think of a Merkel tree as a binary tree as shown here. Now it starts from the root node and each node has two children node. Now each node is associated with a 256-bit integer and the following property follows. The integer of the parent is determined by concatenating the integers of its children and then hashing it. As a result, if we assign certain integers to the leaf nodes, then we can calculate the integers of the previous layer and the previous layer and therefore the whole tree. So one consequence of this is that if I know the integer corresponding to the root node, which is the topmost node, then there is no practical way to find the integers associated with each node such that the final integer corresponding to the root node is the given integer, because we know that it is practically impossible to find an integer such that its hash goes to a particular integer. So therefore, once someone creates a Merkel tree, then it is practically impossible to create another Merkel tree which has the same root node. Now in proof of reserves, this is what the exchange does. Now it creates a Merkel tree where the leaf nodes correspond to each account, and for each of the leaf node it creates the 256-bit integer by hashing the balance of each account. Now that it has integers for each of the leaf nodes, it will create the Merkel tree and it will find the topmost root node's integer, also known as the root hash. Now the exchange will share this Merkel tree with an auditing agency. Note that the exchange does not share your personal information with the auditing agency. It only shares this Merkel tree, which consists of random 256-bit integers. Now, once the agency approves that the exchange has sufficient balance for each of the hash, which corresponds to some account, now you as an account holder can verify whether your account existed in the snapshot of the Merkel tree. And how to do that? Simply, you can hash your account and then you can find the 256-bit value corresponding to your account, and you can check whether that 256-bit integer existed in the Merkel tree or not. So this way, the auditing agency has verified the proof of solvency of the exchange without getting access to your data. And you can verify that the exchange actually gave the proof of solvency for your account to the auditing agency. So that's all for today. Hope you found this video insightful and interesting. And if you are new to this channel, then subscribe to MacroHard, where we are building the next economy. So see you guys tomorrow, and until then, bye bye.